Hello viewers, in this session I would like to discuss on the validation of time period and base year with STAAD Pro. So before that I will start discussing on the considered structure with a manual calculation. So later on the same output whatever we are getting in the time period and base year in the manual calculation should be similar in the STAAD Pro. So here in this STAAD Pro I am using the Connect Edition which is the latest one, right? So for this particular analysis I am going to consider the structure with an elevation of 12 meter. You can see in this image. So if you refer this, if I calculate the slab weight, means what I am going to is I am going to take the self weight of the structure first, which is required for the seismic analysis. So if you are willing to understand the seismic analysis of a structure, so please do comment so that I can do one more video on that particular part. So calculation of this base shear. So base shear VB which is H into W, right? So which is provided in IS 1893, IS 1893 2016. I am referring 2016 part 1. So in this we can see that VB is equal to VB is base shear and AH is the horizontal acceleration and W is the seismic weight of the structure. So seismic weight of the structure, that includes weight of slab, right, and weight of beam, right, and weight of columns, right, and weight of walls, right, and live load. So the code has given some recommendations or considerations to in the part of a live load on the structure, whether it is on the roof or on the floor levels, it is quite different. So if you need then I could discuss on that part referring to the codal provisions. So here I would be concentrating on the calculations of this part in a manual, and later I am concentrating on the STAAD Pro version. So AH is nothing but Z by 2 and I by R and SA by G. So Z is the zone factor in which zone the structure is located, and I is the importance factor, R is the moment reduction factor, and SA by G is refers to the ground acceleration referring to the type of soil below the structure. So now in this considered structure, the Z, everything will be known, right, before that. So Z is a third zone I am going to consider, and live load on the structure is 3 kilonewton per square meter. If it exceeds and if it is below the 3 kilonewton, then there is a difference in considerations of in the calculations. So when it is up to the 3 kilonewton per square meter on the floors, it is 25% is to be considered. And then size of the column, which is 450 mm by 450 mm, and size of beam, it is 250 by 400 mm. So practically it is impossible. So for calculation purpose I am considering this. Later we can do iterate. And the thickness of slab thickness, which is 150 mm, and wall thickness is 230 mm, sorry 120 mm we can take, which is partition wall like, and importance factor 1, and the structure type which is OMRF. So OMRF is ordinary moment resisting frame, and there is one more thing which is SMRF, that is special moment resisting frame. So particularly structure is provided with ordinary moment resisting frames. So now as a calculation part, if I consider for the slab which is having 150 mm thickness, so considering the unit weight of slab. So if you see, plan dimension are 7.5 meter at 22.5 meter by 22.5, because 7.5 meter is a each bay distance. There are 3 bays with 22.5 meter of total in both directions. So that is the floor area, right? And for concrete I am going to take the 25 density, and for masonry I am going to take 22.5 kilonewton per meter cube. So for slab, if I consider 22.5 on both direction with a 25 density and with 0.15 thickness, so this comes out to be 1898.40 kilonewton. So in a similar way, if I calculate it for beam on the either side, considering in both directions and considering the dimensions of 250 by 400 mm for a 25 density, it comes out to be 450 kilonewton. So you can calculate it, right? And for column it comes out to be 243 kilonewton, and then for walls it comes out to be 648 kilonewton. So for live load, 25% is to be considered, since it is 3 kilonewton load, it is 380 kilonewton, right? So referring to this, so total load, overall load on the structure will be 13650. So whatever these parts are considered, this is for one floor. So there are 3 numbers of floors, alright. So for one floor it will be of 3619 kilonewtons, right? On the slab we need not to consider the wall load, right? So I hope you know the manual calculation of this. So if you do not know, please let me know so that I can cover that part too. So out of this, if I calculate the total seismic weight of a structure, which is 13650.5 kilonewtons. So this is what the total seismic weight of the structure. So now time period, if I want to calculate, which is 0.09 times d h divided by root d. So this is what we have for RC structural frames or for all other type of structure. So here 0.09 h is the height of the structure, h is 12 meter, and d is the least lateral dimension if I need to take. So on the both lateral dimensions are 22.5 only, so it is 22.5. it comes out to be 0.277. So this is what we need to get in the software after modeling this. So later on for SA by G, considering the medium stiff soil and considering the time period, we will be having 2.5, right, and I is 1, right, and Z is 3. So the value for Z referring to the code, it is 0.16, right. So later on what we have R, which is ordinary moment resisting frame, which is 3. So everything it is there in the code book, you can refer that from IS 1893 2016. So after this, after all substituting this SAYG in this particular AH, so AH comes out to be 0.0667. So this is the value we need to get in the software AH, and this is the value we need to get in the software seismic weight. So once we get the seismic weight and horizontal acceleration and the time period correctly, so that we can able to calculate the base shear, right, this base shear. So once we know the base shear, we can calculate the total distribution of this base shear throughout the floor levels. So VB comes out to be 910.03, you can say 03 kilonewton. So this is what the total base shear of the structure, right? So which comes out to be from the referred plan and elevation of the structure. Referring to this, we need to calculate each floor levels, whatever the base shear we have calculated 910.03 kilonewton, that should be distributed through the each floor level, right? So if it is distributed through each floor level, if I write for fourth floor, for third floor, for second and first, so it is distributed like 426.53 in kilonewtons. So I will show these values in a software output. So 737.35 and 426.53 kilonewton, and then 310.83 kilonewton, and 138.14 kilonewton, and 34.54 kilonewtons. So these are the forces at each floor in a lateral direction due to seismic load. So once we are able to get this through the software, then it is confirmed that the manual calculations and the software output is validated. So now I am going to start this part. So in this I am going to take the Connect Edition version. So multi-story structure I am going to name it. I am going to save the all the folders in a particular location, and analytical model I am going to take this metric unit. Then I am going to create the structure. So while creating this, I would like to take this structural wizard, since the dimensions are in symmetric direct way. So frame structures, you can see it is a feet in length, so I need to change this to meters, and then I can enter. So length, it is 22.5, and height it is 12 meter. Yes, there are 4 floors of 3 meter in height, and it is 22.5. So in along the bay we have 3 numbers, along the height we have 4, along the width I have 3. So if you can go back and check the plan dimensions, then if you apply, this is the structure. In both direction we have 3 bays of 7.5 meter in each. So I am going to copy this structure. So I will just check out the dimensions. It is 7.5 meter in each bay and each direction, and you can see on the either direction it is having similar, and in the plan it is 3 meter, right, and having 4 floors, right. So it is confirmed that the dimensions are similar. Then I will start creating the model. So in the properties, if I define the structural dimensions, so first I am going to take this column. So column having the dimensions of 0.45 by 0.45, right, and I have a beam section. In depth it is 0.4, and in the width it is 0.25, right. So now this is what the structural dimensions that they have given, and if I want, I need to apply, assign these to the columns. So 0.45 is for a column. I'm going to select the parallel directions and assigning it, and here I'm going to assign for the beam dimensions, and just assigning it, and then I will go to the supports directly, creating the support of a fixed end condition. It is easy if you take in a front view, so that I can select all the supports at a time and assign to the selected nodes, and then I am going to assign it a fixed end support. So the major part which comes out in a loading. So in loading, when we are performing seismic analysis, always we must go for this definition part. So since we are doing it a seismic definition, I am considering this seismic definition. Here I will take the code of IS 1893 part 1 2016, so that I can input all the seismic parameters. So here in this part I have considered the zones. Zone is 3, as we have discussed. The zone factor value is 0.16, and response reduction factor is, here you can see, RC building with ordinary moment resisting frame, which is 3. So these values 0.16, 3, and importance factor, it is as all other buildings, that is 1. We are using this to calculate horizontal acceleration AH, and the soil type is medium, and structure type is building with RC structure. So it is generated, and then I am going to add it. After this, I need to add a floor load. So in this floor load, if you consider, we have live load of 3 kilonewton per square meter, and we have a slab. So if you calculate the slab load, it is 150 mm, which is 0.15 meter into 25 density per square meter of area, means it comes out to be 3.75. How did I calculate this one? It is, so I can show this, it is 0.15 times 1 meter on length and 1 meter in width, and density, it is 3.75. So this 3.75 in Y range, it is 12 meter height. So I will take the cover of 13 meter height. So whatever the floor levels which comes between 0 to 13 will be assigned with this 3.75, and in the X range it is 22.5. so that I will take, it is 23, so that it will cover completely, or you can take 22.5 directly. So which I have assigned now, which is only the weight of slab. So now I am going to assign this 3 kilonewton load, live load, add it, because the Y range, X range and Z ranges are similar. So once I do this, I am complete with this seismic definition. Then I will go for this load calculation considerations. So before considering this load, I need to go for this dead load, first seismic load. So because whenever we are considering this definition of as a seismic part, the load case value should start with seismic itself. Seismic load. Seismic load in X direction I will take first, and then seismic load in Z direction I will take. After that I will go for dead load. After that I am going for this dead load, and later I am going for live load. Alright, and then I will close it. So in seismic direction, in the X direction I am going to add it. So if I consider seismic load in X direction, the factor is 1, I am going to select that thing. In seismic Z direction I will go to select the Z direction and then add. In dead load, first I need to consider the self weight of the structure, later floor load. So floor load, it is minus 3.75, it is the self weight or dead load of the slab, because we have not modeled that slab part in a model, so that I cannot consider that in a self weight, so that I am entering externally the load values. So in a Y range it is 13, in X range it is 23, and in Z range also it is 23. So I will assign this self weight to the whole structure, and then go for live load. In live load seismic, in floor load it is minus 3 for the height of 13, width 23 range, and another direction width it is 23. So now which is been modeled. So here you can consider the load combination, defining the combination. Either you can consider for auto load combination referring to IS456 here, IS456 table number 18, or else you can directly define yourself manually, so that here the default load factor is 1 or 1.5, like dead load plus live load into 1.5, that is taking the 50% extra for that part, and 0.9 times of dead load and live load is there. So you can refer the IS code table number 18 by referring to this, or else defining this one, I am going to take this dead load and live load, so the factor is 1. I will just add it. So now what I have done, the combinations of the load cases are this one. So now I have completed the modeling and assigned all the loads on the structure. Now I am going to analyze it. So in the analysis, if I done this one, then I will go for run analysis. I need to wait for seconds. So once it is done, go for post processing mode, and then I will consider this combination to be applied on a structure. So once it is done, here in utilities we can take a look of this seismic parameters. You can see now. So here the time period for a structure, it is 0.22768 seconds, which we have calculated here in this here you can see 0.22. this is what, okay. I hope you are getting this one. And here this is AH VB, which is equal to 0.0067, and this is total W. So and the value of 910 kilonewton is the total base shear, right? So if you refer that, you can see 0.67 AH, right? It is validated, the time period is validated, right? And the base shear 910 is validated, right? So all the data are considered in the modeling, whatever we have calculated manually. So the similar thing is considered observed the output through the manual calculations. So later on you can see the distributions through floor levels. So at floor level 3, so it is 30.375, right? You just need to remember this, and you can compare to this the 6th meter height at floor level 3, it is 121, and at this level it is 273, and at this level it is 485. So these are the floor level distribution of the lateral forces for the structure. In X direction it is, and similarly in a Z direction we have taken, it is also showing the similar values, 121 and 273 and 485, right? So this is what the output which we can expect from the seismic analysis when we are comparing with manual calculations and the STAAD Pro output. I hope you got this concept. If you got any confusions, or if you need any clarifications on these particular calculations, please do comment and share it, so that I can give some more clarification on this part. Thank you.